Hey guys, Tiny Maths here, back with another lesson. Today we are looking at how to convert recurring decimals to fractions. We'll be converting these examples. A recurring decimal is a number where, after the decimal point, there is a pattern of numbers that repeats over and over again forever. In recurring decimal notation, you put a small dash above the beginning and ending numbers of the repeating pattern. So these numbers can be rewritten as the numbers below them. There are two types of these numbers. Firstly, where the numbers start repeating immediately after the decimal point, as you can see in these two numbers. And then, as you can see in these two other numbers, where there are some non-recurring numbers between the decimal point and the recurring decimals themselves. There are two slightly different methods for converting these two types of numbers to fractions, and we'll be looking at both methods. So let's take the first example, 0.62 recurring. There are 4 steps to converting a number like this to a fraction. In step 1, you check the length of the recurring pattern. That is, how many numbers are in the repeating pattern. There are 2 repeating patterns in this recurring pattern. In step 2, we take 10 to the power of the number we got in step 1, so 10 to the power of 2, and multiply it by the recurring decimal. That gives us 10 to the power of 2 times 0.62 recurring. Since 10 to the power of 2 equals 100, we can rewrite this as 100 times 0.62 recurring. This shifts the decimal 2 places to the right, giving us 62.62 recurring. Remember that the numbers repeat forever after the decimal point, so even if you change the position of the decimal point, although the number's value changes, the numbers after the decimals go on forever anyway, so you still have recurring decimals. So now we have an equation with two numbers that have the same recurring pattern after the decimal point. If we subtract one of these numbers from the other, we can eliminate the recurring decimals altogether. And this will help make it easier to work on the problem. In step 3, label the original number with recurring decimals as x. So x equals 0.62 recurring. Now, 62.62 recurring is 100 times 0.62 recurring. So that's the same as 100 times x. So we can label that as 100x equals 62.62 recurring. In step 4, we make a two-sided equation. On the left-hand side, we'll work on the x values, and on the right-hand side, we'll work on their equivalent numerical values. What we have to do on the left-hand side is subtract the smaller value from the larger value. So you have 100x minus x. And do the same with the equivalent values on the right-hand side, which gives 62.62 recurring minus 0.62 recurring. 100x minus x equals 99x. So let's rewrite this on the left-hand side. What about the right-hand side? Well, we can look at 62.62 recurring as 60 plus 0.62 recurring. And on the right-hand side, we are subtracting 0.62 recurring from that. And the recurring decimals cancel. So that would leave us with 62. In step 5, we just need to isolate the x by dividing both sides by 99. And that gives us x equals 62 over 99. Of course, we know what the numerical value of x is. X equals 0.62 recurring, our original recurring decimal. So replacing x with that gives 0.62 recurring equals 62 over 99, and there you have it. The recurring decimal has been converted to a fraction. On a side note, if you were given a number like this to convert to a fraction, you can simply set the whole number aside. So separate the number into two parts, 3 plus 0.62 recurring, and convert the recurring decimal to 62 over 99, which is a fraction, and rewrite this as 3 plus 62 over 99. And of course, that's the same as 3 and 62 over 99, which is a mixed number. So you only need to work on the decimal part and just add it to the whole number after conversion. So you can use this method for any number that you are given that is of this form, that is a whole number followed by recurring decimals. Anyway, we've dealt with the first scenario. Let's now work on our other situation where the recurring decimals are preceded by some non-repeating decimals. Let's use 0.2762 with the 62 recurring. In step 1, we have to make a note of two numbers this side. First, we check the length of the recurring pattern. Well, again, that's just 2 because there are only two numbers repeating. But then we also have to make a note of how many non-repeating decimals there are, and that's 2 also. In step 2, we're going to take 10 to the power of two different numbers. Firstly, 10 to the power of the number of non-repeating decimals, which is 10 to the power of 2, and then 10 to the power of the sum of non-repeating decimals and repeating decimals. That sum is 2 plus 2, which is 4, so we're taking 10 to the power of 4. Now, with this 10 to the power of 2 and 10 to the power of 4, which equals 100 and 10,000 respectively, we multiply them both by the recurring decimal. And this gives us two equations. 100 times our recurring decimal, which gives us 27.62 recurring, and 10,000 times the recurring decimal, which gives us 2,762.62 recurring. Step 3, we label each of these numbers. We label our original x, so x is our recurring decimal, and then since 27.62 recurring is 100 times the recurring decimal, we'll label that 100x. And since 2,762.62 recurring is 10,000 times our original recurring decimal, we'll label that 10,000x. So 100x equals 27.62 recurring, and 10,000x equals 2,762.62 recurring. In step 4, we make a two-sided equation again with the x values on the left-hand side and the numerical equivalents on the right-hand side. We take the two largest x values and subtract the smaller one from the larger one, and that gives us 10,000x minus 100x. And on the right-hand side, we represent this with their numerical equivalents. So that's 2,762.62 recurring minus 27.62 recurring. The left-hand side results in 9,900x, and on the right-hand side, the recurring decimals cancel, and we are left with 2,762 minus 27, and that gives 2,735. So 9,900x equals 2,735. Finally, for step 5, we want the value x, and we can do this by dividing both sides by 9,900, which gives us x equals 2,735 over 9,900, and of course x is our original decimal, so the original decimal has been converted to the fraction 2,735 over 9,900. Now you may be wondering why in our second example we didn't just do 100x minus x. Well, look what happens if we try that. 100x equals 27.62 recurring, and x is our original decimal 0.27 with 62 continuously recurring forever after that. For these two numbers, the numbers after the decimals differ slightly. So when subtracting x from 100x, we can't just cancel the numbers after the decimal point because they are not exactly the same number. You'll need to do some extra work after subtracting. It is doable, but I like to keep things simple. So instead, we can just multiply the original recurring decimal again in a way that creates an even larger number, but one that still has the same recurring pattern after the decimal. You would then have two numbers, both with the same recurring decimals, which will cancel, and that will make your numbers easier to work with. Let's do one final example, which is going to show you why using only one multiplication and doing doing 100x minus x won't work for a particular recurring decimal. Let's take this number. In step 1, we check the length of the recurring pattern. Its length is 3 because there are 3 numbers that repeat over and over again. Then we check how many numbers are non-recurring after the decimal. Well, that's 2, 1, so that's just 2. For step 2, we create two powers of 10. First, 10 to the power of the number of non-repeating decimals, that's 10 to the power of 2, which equals 100. Then 10 to the power of the sum of non-recurring decimals and recurring decimals, and that's 10 to the power of 2 plus 3, which is 10 to the power of 5, which equals 100,000. We then generate two numbers by multiplying the recurring decimal by each of these two powers of 10. So we get 10 to the power of 2 times the recurring decimal, which is 100 times the recurring decimal, and we get 10 to the power of 5 times the recurring decimal, which is 100,000 times the recurring decimal. These two results give us 21.586 recurring and 2105.86.586 recurring. So now we have three numbers: the original recurring decimal, one which is 100 times the recurring decimal, another which is 100,000 times the original recurring decimal. For step 3, we label all three numbers. The original with x, so x equals our recurring decimal, and then the one which is 100 times larger with 100x, and then the one which is 100,000 times larger with 100,000x. In step 4, we make the two-sided equation with the x values on the left-hand side and subtract 100x from 100,000x. This gives us 99,900x. We do the same with the numerical equivalent on the right-hand side, which gives us 21,586.586 recurring minus 21.586 recurring. The recurring decimals cancel, and that leaves us 21,586 minus 21, and that equals 21,565. So we have 99,900x equals 21,565. Finally, in step 5, we isolate x by dividing both sides by 99,900, and that gives us x equals 21,565 over 99,900. And finally, we replace x with the original value, the recurring decimal. So we get that the recurring decimal equals 21,565 over 99,900, and our recurring decimal is converted to a fraction. We can see again why 100x minus x would not work immediately, because that would be 21.586 recurring minus 0.21586,586 and so on. This time it's even worse because none of these decimals match up, making it even more difficult to work things out. So it is best practice to get two numbers, one larger than the other, but they have just the recurring decimals after the decimal point. And you can achieve that by using the methods that we looked at in example 2 and the previous example. You probably noticed that I haven't attempted to simplify any of these resulting fractions. In the last example, the recurring decimal resulted in the fraction 21,565 over 99,900, which is pretty hard to simplify. I haven't actually done the simplification of this fraction because that would make the video very long, and you can use your calculator anyway to demonstrate that this fraction is equal to the original recurring decimal. I doubt your teachers will be asking you to simplify a fraction like this because it's not necessary really. I mean, the the primary purpose of doing exercises like this is for you to be able to express the recurring decimal in terms of a fraction. So you can always use your calculator if needed. Of course, you could actually try to simplify these fractions just as an experiment for yourself to see if you could do it. It would be a good exercise to give you some practice. I've made another video that shows you how to use prime factorization and other methods for simplifying fractions, so perhaps you want to go and check that out for a refresher if you're going to attempt to simplify these fractions. Well, that was quite a long lesson, but we had a lot to cover. Feel free to watch again if you need to, because I know it was a lot to take in. Well, that's it for now. We'll see you in the next video. Take care.